Physics of weaponry. Oh, this looks interesting.
What is the meaning of life? Well, there's a song by Metallica called "To Live is to Die." Then what causes death? Things like weapons, which is the topic of this video, specifically the physics of weapons. To begin with, what is a weapon? A weapon can be defined as any implement or device that is used to deter, threaten, inflict physical damage, harm, or kill. But since this is such a broad topic, I'll only talk about handheld weapons. For example, sticks and stones, a bat, a knife, a bow and arrow, and so on. Among these weapons, I'll split them up into 3 categories, that being blunt, sharp, and ranged weapons. Starting off with blunt weapons, take a look at this stick. Now watch as I demonstrate its use as a weapon on my imaginary friend Bob over here. Now, why did that hurt exactly? And no, it's not because I'm so strong, even though I am. It's because I'm using something called a lever. What are levers, you may ask? A lever is a simple machine made of a rigid bar that pivots on something called a fulcrum. There are 3 types of levers, and the difference between them depends on what's in the middle. As you can see in the first example, the fulcrum is in the middle, and the effort and the load are at the sides, making this a first-class lever. In the second example, the load is in the middle, and the fulcrum and effort are on the sides, making this a second-class lever. And the important one for this video, the third-class lever, the effort is in the middle, and the fulcrum and load are on the sides. Third-class levers are used in mainly every melee weapon and are quite effective. Why, though? Because unlike the first and second-class levers, the third-class lever amplifies speed and distance, 2 things that are quite important when you're fighting someone. But due to the load being on the end of the arm, the resistance arm will always be greater than the effort arm, which makes moving the load using this type of lever always require more force than it would using these 2 levers or just lifting it up normally. Luckily, this is usually not an issue regarding weapons, as they're made to be lightweight enough to actually use, like this baseball bat, for example. Now, it's not actually made to be a weapon, but still is used as one. Hammers are also weapons sometimes, and are a great example of a third-class lever. Here, your wrist is the fulcrum, the load is the head of the hammer, and the effort is the muscles that contract to make that rotational movement in the wrist. Of course, when swinging a hammer or any weapon, it's not just the wrist, but the elbow and the shoulder as well, which are also fulcrums of third-class levers. Your body is full of these, by the way, and even though these levers require more force than the other 2, the speed and distance advantage just makes it worth it. Now, here's a question. If I have a baseball bat longer than our solar system, and I swing it like so, could the end of the bat surpass the speed of light? No. Even if the bat was made of diamond or the core of a neutron star, it would break due to the flexing in its structure. There is no perfectly rigid material in the universe that would allow energy to be transported faster than light. And while I'm still on the topic of levers, let's talk about torque. Now, what is torque and how does it relate to weapons? Torque is a measurement of the force which causes something to rotate around a point. Here's the formula, with torque being equal to the radius multiplied by the force. Put simply, the longer the radius is of the force from the fulcrum, the greater the torque is, which is the rotational force, and vice versa, with meaning a smaller radius, lesser torque, lesser rotational force. For example, look at this door. Rotating it by the handle is easy, but rotating it closer to the hinge is hard because there's less distance from the fulcrum, less torque, and therefore less rotational force. Torque is relevant in weapons that are particularly long or heavy, and so they tend to have grips or long handles that work to apply more torque to counter its mass, like polearms or spears or staffs. Anyways, on to the next topic of weaponry, sharp weapons. Blades like this kitchen knife work by using their sharpness to focus force into a tiny area, which creates an immense pressure that allows a cut to be made. So then, what actually defines sharpness? Well, you could answer with pointiness and narrowness. If we zoom in to the edge of the blade, called the apex, there is a curve at the very end, which can be extended into a circle. The radius of that circle defines the blade's pointiness and is called the edge radius. The narrowness of the blade is determined by the angle between the two flat sides of the wedge, meaning a smaller angle gives a thinner wedge with a usually sharper blade. Sharpness can also be defined as the amount of force we need to cut something. And this makes sense because, of course, a sharper blade should cut easier than a dull blade. But sharpness actually has much more variables than edge radius, wedge angle, and the amount of force needed to cut. You also have to take into consideration the shape of the tool, the speed, its angle, and the material being cut. This kitchen knife, for example, is relatively sharp, but only if I'm cutting something soft and putting a lot of effort into slicing or stabbing. With a sword like this, it acts like a third-class lever, so that the distance and speed are also amplified and therefore its sharpness as well. And because the sword has much more significant amount of mass than the knife, it also has a greater inertia, and should be harder to stop as well, allowing it to cleave through things better than the small knife. Now, look at this karambit. It has an interesting shape, right? Like the claw of a T-Rex. Unlike other blades that are often used for straight slicing or stabbing, the curve of this blade is used to hook, pull, and slice easier. Depending on the situation or material being cut, different blades can be more beneficial than others when fighting. Though, I would not recommend bringing a blade to school, or actually any weapon, especially the next type of weapons that I'll be talking about. Ranged weapons. Ranged weapons can vary a lot in how they shoot projectiles, but usually it's through potential energy in some form. This is most evident in things like bows and crossbows, slingshots, where elastic potential energy is used to propel the projectile. But how does this elastic potential energy compare to the energy in the human arm and body? How does an arrow compare to the ancient projectile weapon that was used against Jesus himself? Here I am at my local park to test out projectile weapons. Which weapons exactly? The bow and arrow, as you can see, and a simple rock. First, I'll test out these two rocks. Okay. Unfortunately, I couldn't find my second rock. But I did find my first rock, which ended up about 90 feet away from where I threw it. So, on to the bow and arrow test. So, the first arrow ended up about 105 feet away from where I shot. And as for the second arrow, I couldn't find it. Moving on. From that test, I found my rock throw to be around 90 feet, and the arrow from the bow to be about 105 feet. So which projectile took more force to launch? They actually took roughly the same amount of force, but if I was using an actual hunting bow rather than a children's bow, it would probably be the bow that would take more force. Here's a Desmos graph of the roughly estimated trajectories of the arrow and the rock. One small square is equal to 1 square meter. Despite the two projectiles being launched with a similar force and angle, the arrow ended up 15 feet farther than the stone. What helped was the arrow's long, thin, cylindrical shape, which allowed it to penetrate through the air more easily than a jagged rock. And so to conclude this experiment, the arrow has superior aerodynamics and greater penetrating power as well. So now, what do you think is the most efficient ranged weapon? By that I mean, what handheld ranged weapon has the greatest ratio of force input to force output.
Isn't it the thing that goes pew pew pew?
That's right. It's a... It's a gun. What makes firearms special from the primitive bow is the use of a barrel, a propellant like gunpowder, and an ignition agent. Here's a quick summary of the physics behind the gun. You first pull the trigger, which releases a spring-loaded hammer or striker, which hits the primer of a bullet. For example, here's a bullet casing, and here's the primer. And that ignites the gunpowder inside of it, which then propels the bullet through the barrel with expanding high-pressure gas, leaving you with a bullet traveling at a terrifying speed. Speed that turns a tiny piece of metal, lighter than a dozen grams, into a projectile capable of killing people hundreds of yards away. As opposed to a bow and arrow and its elastic potential energy, a gun's chemical potential energy within the gunpowder and the ingenuity of the gun makes it the ultimate weapon, and is why guns are so widespread and popular in the modern day. Anyways, have you ever wondered why some weapons spin?
I'll try spinning. That's a good trick.
Spinning increases the angular momentum of a weapon and can make something harder to stop than moving it normally. Angular momentum is similar to linear momentum, where momentum is equal to mass times velocity, but instead of multiplying mass and velocity, angular momentum is equal to the moment of inertia multiplied by the angular velocity. All you need to know about the moment of inertia is that it's the equivalent of mass from the linear momentum formula, and it's also calculated in a bit more complicated way. With all that in mind, look at these homemade nunchucks. Swinging them at someone normally would cause pain, but swinging them and then spinning them would cause even more pain due to angular momentum. Shurikens are also weapons that utilize angular momentum, not only to cut deeper into a target, but to cut through the air more effectively and stabilize itself like a gyroscope. Your average bullet spins as well due to rifling. Rifling is the spiral grooves in the barrel of most guns, and these things can make a bullet spin at over hundreds of thousands of revolutions per minute. With that amount of speed and spin, the angular momentum carries the bullet through a much smoother path with little resistance to anything changing its axis of rotation, that being the direction of the bullet. Of course, wind can affect a bullet's trajectory and shift its axis of rotation ever so slightly, but usually after it already passed over 100 meters or so and lost some of its speed and momentum. And yeah, that's pretty much it. Hopefully you learned something about levers or sharpness or guns and whatnot, and hopefully you're slightly more knowledgeable about the physics of weaponry. Excuse me one moment.
I just watched that video you made and it was incredible. You deserve 100% on that assignment.
100? More like a 0, considering this assignment was due last month. Yeah. Anyways, thanks for watching.